family is driving to Yukon for a family vacation. The graph represents the amount of fuel in the gas tank of their car on the first day of their journey. So, this line is representing the amount of fuel in their car at a given time. I'm just going to scroll down a little bit so I can see the letter word time of day. Looking at this, the fuel goes from 0 up to 60. The time of the day starts at 7 a.m. and it goes until 5 p.m. And that's 17 o'clock, that's military time, right? So you go 17 to 12 to figure out the time, which is 5 p.m. I did a weird connection for right Awesome. If you look at the line is a function of time, which tells you how much fuel you have. At the start of their journey, 7 a.m., they have 50 liters of fuel. That represents the start of their journey. As the time goes on, you notice that their fuel decreases. Makes sense, right? It's going down because I'm driving. I'm going to use my fuel. And then all of a sudden, it hits that elbow right there, and it goes completely flat. At that moment right there, what's going on from B to C?
They're eating Denny's.
Yeah, they're eating Denny's at the gas station or something. Yeah, they're doing something, right? Like the car has stopped moving. That's why the amount of fuel stayed the same. Right? We're losing fuel, and then all of a sudden the fuel never changed. They've stopped somewhere. They're eating Denny's. They're doing something, right? Someone had to go pee. They stopped for about like an hour or so. So like probably eating Denny's. I like that excuse. Then look at from C to D. It goes from here straight up to the gas station. Gas station, right? They filled up their car. That's what that represents. So at point C, they fill the car back up with gas. Boom, they launch all the way up to there. Then they start driving again. As they're driving, it's going down and down and down and down and down and down. And then you hit point E, and they take another break. Probably another Denny's in a different town. Right? So they've stopped somewhere again. They stop for about another hour by the looks of it. And then it keeps going down. So this is them driving again. And then it stops at G and goes straight up. That represents another gas station. Right? So from G to H, they stop from the gas station. Their fuel goes from pretty low to 20 all the way back up to 60. That's a gas station stop. And then they start driving again until they stop their journey right there. That's interpreting a graph. As long as you can realize graphs actually represent things with word problems, you'll be set. And the line is always a representation between two different things. Ours in this one was fuel and time. There's a bunch of questions here. We'll just talk about them. So with reference to the journey, explain what's happening. We already talked about that. From A to B, they're driving. From B to C, we said they're at Denny's. As long as you just say they stop. If they stop somewhere for an hour. And from C to D, that represented gas station. Right? They fueled up. That's all interpreting graphs is. Looking at something, knowing how to kind of follow along and play along with what's happening. You guys did a bunch of this in grade 9. At least you should have done a bunch of like interpreting graphs and mathematics. Yeah. B, I don't really like D. I think it's all hard. It says, what is the rate of fuel consumption from D to E? So if you were to do this for real, I don't think I'll test you on this, but we could. From D to E. If you're trying to figure out fuel consumption, like the rate in which you're using fuel, you need to figure out how much fuel you used and divide it by how long it's been. So if I started at 60 and then I stopped at 30, that means I used 30 liters of fuel. Right? Went from 60 to 30, lost 30 liters of fuel. That's how much I used. Yeah.
This actually
Is it 25? Sorry. That means I actually used 5 liters of fuel. Thank you. Then you're going to divide it by however long you were driving in that amount of time. So if I use 35 liters of fuel and it took me, looking at time, from there to there, that's 1, 2, 3 hours. I would go 35 divided by 3. And that would tell me my rate of fuel consumption. 11.666? So when you hear like commercials and they talk about like fuel consumption, and you always see that and they'll be like, oh, this truck is 8.5 like liters per hour. Like that's telling you how much gas it's burning at a certain speed. They'll always do a highway rate and a city rate because typically you burn more fuel while you're driving in town and less when you're on the highway. Because in town you're constantly having to like slow down, speed up, which burns a lot of fuel. And then on the highway, if you're just like at nice cruise control, it's not so bad. So typically that's how it works out. Sometimes it flips, just depends on who's doing the like studying. Awesome. The next thing we could interpret, we're going to talk about like C. Which line segment represents the car being refueled for the second time? My second refuel was from G to H. That's right here. Right? That's my second refuel. My first refuel was C to D. D, calculate the total time the car is being driven. All right. So we're only going to calculate when it's being driven. I'm going to have to erase some of this stuff here. Awesome. I'll do driven in red. From point A to B, the car is being driven. The gas is going down, right? So that's us driving. Other parts we're driving. D to E, we're driving. Other parts are driving. F to G, and then H to I. So those segments in red are all the different times in which I'm driving. I need to get those colors. Making it too hard to see. Can I do it full on session? Those highlighted areas are where we're driving. If you want to figure out the total amount of time you're driving, you're just going to add up all those segments. Right? So if you're looking at the first segment, they drove from 7 for 1 hour, 2 hours, 3 hours. Then starting at point B, they start driving again for 1 hour, 2 hours, 3 hours, another 3 hours. Then they drive from F to H, so they drive for another hour. Then they fuel up, and they drive for another hour. The total number of hours would be 1, 2, 3, 4, 5, 6, 7, 8 hours of driving. Right? Split up over a couple stops, but it's 8 hours of driving total. That's how you could interpret that graph for driving hours. Last question. If the fuel costs 85 cents per liter, calculate the cost of fuel used for the first day of the journey. If you want to figure out how much it costs to fuel up, you need to figure out how much fuel you used. That's the same idea as what we did before with the x values, but now you're doing it with y values. So if we look at our y values, we're trying to figure out how much gas we used on this trip. We're going to figure out where we started. We started at 50. Then we drove it all the way down to, did you say that was 20? That's 20. From A to B, we used 30 liters. We went from 50 to 20. Then we fueled up, and we were now at 60. and we burned our fuel all the way down to here at G, which appears to be at 15. Is that fair? Yeah, in your books you guys can see better than me probably. So I went from 60 all the way down to 15. If I want to figure out how much gas I used, that would be plus 45. I filled it back up to 60, and I burned it down to I, which appears to be from 60 to 50, so it's plus another 10. That would show all the amount of fuel that I burned. 30 plus 45 plus 10 equals 85 liters of fuel. They wanted to know how much it cost. So if I had 85 liters, and it costs $0.85, 85 cents, I would multiply those two numbers together to figure out the total amount of cost. Anyone punch that in a calculator for me?
72.25.
$72.25. The biggest thing I want you to be able to do is to look at a graph and understand what's happening. Okay, if you can read and understand a graph, you should be pretty well in the clear. Okay. Awesome. There's two questions here. Both represent speed and time. So this one's a speed and then time. We're just going to come up with scenarios where this could happen. Okay, so if you look at A, a possible scenario where I'm now driving fast or I'm moving fast, then I decrease, then I stay at the same speed, then I increase, then I stay at the same speed, then I decrease right down to 0. Yeah.
Baseball pitcher throws it, hits the bat, it slows down and then it stays the same, and then it speeds up, and then a person catches it, and then they throw it at first base.
I like it. And you're saying these are all the different speeds of things when it hits different spots. Yeah, you can do that because you pitch it, it starts off fast, it slows down, gets hit by the bat, so it goes at a certain speed, and then like some point it speeds up, coming back down maybe. Yeah, it speed up, and then guy gets it, throws it, gets caught. Yeah, that would work. I like to always think of things as cars. This is a pretty good representation of driving down Highway 11 right now. So if I'm driving from Red Deer to Sylvan, I'm going like 110. Then I have to slow down for the construction. Right? They got that construction now, so I'm down all the way to 40. That's me slowing down. That's me going 40 through the construction. Then I get to speed up. So I speed back up, but I only get to go up to like 80 because it switches right before those lights. Right? So I get to 80. I'm driving 80 kilometers an hour. Then I slow down for that red light right at the edge of town. Okay? That could represent this situation. Any situation you could come up with where you're at a constant speed, slow down, constant speed, speed up, constant speed, slow down to a stop would work. Anything. It can be driving around town, whatever you want. B is a little bit trickier, especially since it's got like these weird little bumps. Right? So it looks like maybe we're like
Yo-yo.
Yeah, a yo-yo would be a good representation, right? Like this would be the speed of a yo-yo. So it starts in my hand at 0. I throw it down. It kind of like goes fast, and then it slows back down at the bottom, and then it comes back up to me, and then it goes back down. Then it goes back up to me, and it goes back down. And that's like the speed of the actual yo-yo. And it goes fast, slow, fast, slow. That would work. For those bubbles, that's a tricky one. Anything you could come up with a story where you're going to get gradually faster, and then kind of peak, and then slow back down, and then peak, and then slow back down would work. Maybe riding your bike down and up hills would work. And so if I'm going down the hill, I start at the top of the hill, my speed's going to get faster, faster, faster as I'm going down the hill, right? And then I got to come back up the hill. So my speed slows down, slows down, slows down, slows down. Then I'm back at the top of the next hill, and I start coming down the next hill. So I go faster, 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 faster. And then I have to come back up the hill. Slower, 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 slower. And then I go back down the hill again, right? So that could be me riding my bike up and down hills. And I'm going to get faster, slower, faster, slower. Any situation you could come up with where your speed's going to be like that, kind of yo-yoing. And it doesn't have to be like a person running anything. It could be an object, like a yo-yo going up and down. Right? Anything you want would be good with me. Awesome. Oh, it's not letting me go. Go on, computer. Squishy graphs. So we could also take like questions like this and show in a graph what we think it would look like. The first situation says the oven temperature when baking a pie. All right, so if I go to bake a pie and I show up, my oven starts at what temperature? 0, right? So it starts at 0. And the first thing I do if I'm good at my job at cooking or whatever the heck I'm doing at baking a pie is I'm going to preheat my oven. I don't even know that's always the first step. And I'm going to preheat it to like, I don't know, 400 degrees Celsius. That sounds like a lot, but we're going to do that anyway. 400 degrees Fahrenheit sounds much more reasonable. Yeah, 400 Celsius would be very hot. As the temperature is preheating, it starts at 0 and it gradually increases until it hits the temperature I want. Once it hits the temperature I want, it stays at that level until I'm done baking my pie. When I'm done baking my pie, I'm going to shut the oven off. Will it instantly go from 400 to 0? No, right? It's got to cool off. So you're going to stop baking your pie. It's going to cool off until it's back to 0. That is what I would expect a graph to look like for baking a pie when it comes to the temperature of my oven. Preheating, cooking, cooling. And it's kind of gradual, right? I don't just instantly skyrocket up and down. For B, Ben taking part in a 100-meter sprint. So, when you take part in a 100-meter sprint, what's your speed when you start? 0, right? You're stuck. Right there. Then they like shoot the gun, right? And you take off. And you're going to increase fast, right? Because you want to go as fast as you possibly can, so you're going to go right away. You start going fast. It's not straight up because it's not instant, but that's me accelerating really fast. And sprinters usually like they hit their top speed after something like 40 meters, and then they stay at that speed until they're done the race. When they're done the race, go ahead.
Don't like some sprinters like speed up at the end though?
Yeah, like some of them have like that extra push, especially in the 100-meter dash. You guys know who Usain Bolt is, right? Like Usain Bolt, like tall, lanky guy from Jamaica. He breaks all the world records. He's like the thing that makes him so like freakish is like his start time is really good, and that's where most 100-meter sprinters like that's where they win their race is in the first like 3 seconds. But he actually has like an ability to speed up. Like he pushes even harder, which is freakish. That's why he always pulls away from the pack like at the end of races because most guys can't do that. He just has a top end speed that's way higher than anybody else. So yeah, like you could think like, okay, they take off and then maybe they actually increase a little bit more, and that would be fine too. What I wouldn't want to see is that all of a sudden they take off and then they like start waving or something like that, right? Like a sprinter should be going fast. Maybe they are slightly increasing too. Yeah. When done the race, they quickly stop running. Right? We're gonna say like really quickly. But if you've watched a race, they don't just stop. They walk for a bit. Right? So they get to this point, and then they're gonna walk. And then they're gonna sit down. So I speed up really fast, run at that speed, slow down once I've won the race, walk a bit, and then sit down. And take a break or something like that. As long as you could give me some sort of story. So your graph might not look the same as mine if you were to do this on your own, but as long as you had some sort of reasoning behind it, right? I want to see the takeoff. I want to